So this is how such shallow trench isolation process flow goes. We have predefined where the transistors will be placed. This part is where we talk about the advanced devices and processes, and also about scaling of integrated circuits. First, I'm going to go through several processes and devices. Then we will see the overview and all the different improvements in scaling, what has happened over the time, and then I focus on 5 or so specific problems and challenges related to scaling for MOSFET transistor. So let's start with the so-called triple well CMOS process. Today, it's not considered very special advanced thing, but back some decades ago, that was a really great thing to have available. And even nowadays, sometimes we will have this triple process, or if we want to pay less for the wafer, we don't have it. What have we got here? So normally, when we talk about CMOS, the PMOS and NMOS transistors, we had them in P-type substrate. And the P-type substrate at the same time was bulk for the NMOS transistor. Imagine if we have lots of NMOS transistors, and for some reason, to adjust the threshold, we would like to change the bulk source voltage. We would change it for all the transistors. That might be the motivation for digital circuits, that it would be okay to change for all the transistors. It's rarely done, but that's a possibility. For analog circuits in particular, it's difficult because if we have, for example, N-channel source follower looks has the source where the signal goes from the gate to the next stage, and then this source is moving. So the source potential is moving, whereas the bulk potential is fixed. So we always experience the threshold variation depending on the DC level of the signal, and that's something we might not want to have. So what helps us is this so-called triple well process, where we have the P-type substrate, then the P-channel transistor is done as usual with N-well diffused into the substrate. But for P-channel transistor, for N-channel transistor, we have a deep N-well that goes maybe 2 micrometers into the substrate. Then we have a shallow P-well, and in this P-well we have N-channel transistor. Now if we want to have several N-channel transistors with different bias of the body, then we can connect them to separate potentials, and it's not everything shorted, and also the bulk doesn't have to be at the substrate level. So we have the isolated diodes. The next improvement that I would also like to point out in a dedicated slide, that's something that it's a norm nowadays, but it didn't used to be, is the shallow trench isolation. So what we have seen in the previous slides, very often I drew PMOS and NMOS transistor in a single die, and then there was nothing in between. That was a simplification. For years, we had a so-called locus, which was an oxide layer, which was not really good for planar realization of the circuit. So we were talking about this planarization, where everything we would like to be very flat. And this old technology was not good enough, and also was not going far enough into the substrates to enable really good isolation. So the new development from locus is this STI, and what we see that everywhere where we don't have gate and we don't have P or N diffusion, all the rest of spaces are filled with this STI. That is, it could be like silicon dioxide, but more often it will be silicon nitride with a layer of silicon dioxide. And we see it's being everywhere, and this prevents leakage currents between the transistors. It also helps with reducing the latch-up probability, although it's still not sufficient. We need to do much more against latch-up. So this is how such shallow trench isolation process flow goes. We have predefined where the transistors will be placed. And it's not very self-aligned like the gate self-aligning technology that you might recall. But everywhere where we know it's not going to be a transistor, it's not going to be a polyresistor or diffusion resistor, because this P+ region or the polysilicon we can also use as a resistor since they have certain defined resistance, so and low resistance. Then all those remaining places we fill in with STI, the insulation. Then in step 5, you can see the N-well is added. And in step 6, well, it's simplified step 6 because everything comes after, basically, all the rest of the processing steps. So these were some of the developments, but over the years, since now 75 years ago, the first transistors were developed. They were bipolar transistors. The concept of the field effect transistor came also around that time. They were in production a bit later as MOSFETs. Then we see here as a function of the time, we have years. Every decade there is a single mark. And then we have a scaling of the characteristic dimensions. So on the y-axis. I didn't add title of this y-axis because it also changes a little bit over time how we define the technology node. For a long time, somewhere between the 70s and 2000, for this approximately 30 years, the technology node was telling us what is the minimum channel that we can produce, the minimum channel length. But before, for the bipolar technologies, it's not an obvious thing how we define it. And also nowadays in the modern technologies, when we talk about, for example, 7 nanometer, it doesn't mean exactly that the channel length is 7 nanometer. So if you are interested, you can go into the specific definitions, but generally it's mostly related to the density of the transistors per unit area, because the microelectronic industry really likes to show that they are still able to follow the Moore's law. Still here, looking at the dimensions roughly, it's more what we can think of in terms of also of the device fabrication. That's what I like to discuss with you in this lecture, so that's why on the y-axis it's the dimension. But please keep in mind it's not quite so strict, the meaning. So what we have then in the 70s, self-aligned gate, and also what was enabled in the late 70s is the ion implantation. That's something that we cannot imagine live anymore, production of semiconductors. And thanks to the ion implantation, first we were able to see the CMOS technology. LDD is the lightly doped drain region. It's something that I didn't talk in detail, but it's really important in order to reduce the high, strong electric fields in the device, reducing the reliability. We have this, for example, in p-channel transistor, drain is P source and P drain, but also we have an extended layer under the gate of just lightly doped P. And that changes a lot the electric field distribution in the transistor. And it's also a topic which you can find lots of information in the literature. Then silicided gate, polysilicon with silicidation, is something which enabled reducing the resistivity of polysilicon. And that's something that was also important for the speed of the circuits. Then trench isolation, shallow trench isolation. We have seen example of how the process looks like. Then we can see here the copper interconnections. That's one more thing that I'm going to still highlight. In scaling, what we have seen is that the power density decreases, the transistor scales down, the metallization also is getting more narrow, but the power consumption is still very high, and we don't want to have high power dissipation in the wires. So one thing what could be done is getting a metal material which has better conductivity. Then halo implant. I'm going to speak a little bit more in just a couple of minutes. That's to reduce the drain source leakage currents. High HKMG, so high dielectric constant metal gate. Then FinFET, multiple patterning, and EUV, so about HKMG and FinFET again, and channel strain. I'm going to speak a little bit more in individual slides. Regarding the last 2 points, when we go down to sub 14 nanometer technologies, then photolithography with ultraviolet, it's not enough. We need extreme ultraviolet, 13.5 nanometer wavelength. But before that was possible, just 2 years ago entering in production, so let's say 2 years ago, about 2021, we were able to solve this fine resolving of the pattern of the transistor with over 100 nanometer wavelength of the UV lasers by doing the multiple patterning. So maybe double patterning was done before, but multiple patterning with triple or more was also the new development. I have added some links in the corner to websites where you can find, so article from IEEE Spectrum where you can find some more information about these scaling processes and many more resources you can find. So directly on the scaling, we can also analyze the interesting topic of how the transistor oxide parameter and transconductance would be changing. So generally, transconductance we would like to keep constant. Threshold voltage we would like to scale down because the power supply decreases. And so mainly the oxide we would like to adjust correspondingly. And here is the list of the, I find, the most important issues that have driven the technology, the scaling of the technology and new developments, as we have seen in the previous slides. So what you can see in this table is the related IC region, mainly transistors, but also the interconnections. Then the issue that we have observed there, and then the solution. For each of them, I'm going to show in individual slide a little bit more detail, but let's have a look first on this overview. So the channel of the transistor gets more and more narrow and more short. And both have some consequences. So narrow channel means that the threshold voltage is not anymore uniform, and the gate will not be seen anymore as a parallel plate capacitor, with the solution that we should go to FinFET. Then higher drain source leakage current is and the velocity saturation, they are both effects of shortening channel length. The fact that we scale also and need to keep the oxide capacitance at the right level means that the charge carriers tunneling is possible through the gate because the gate is being so thin. And finally, for the interconnections, the wire dimensions, they are decreasing, and also spacing is decreasing. So we have a higher resistance of the wire per unit length if we want to take the minimum length of the wire. And also 2 wires are closer together, causing more capacitance between the 2 wires. Let's say if one is shielding the ground, we have capacitance to ground, but it could be cross-coupling between 2 signals, and that's also problematic. So regarding the first point, the non-uniform threshold, because the width of the transistor is getting narrower, what we have is that the threshold voltage is a function of the gate capacitance. That's something that we have seen in the previous units. And at the edge of the, it's not an infinite parallel plate capacitor, but it has this edge effect. And when we make the transistor narrower, these edge effects where the effective capacitance, if we make a lamp model with multiple parallel capacitances representing this transistor, then at the edge, the capacitance would be slightly lower. And then what we see is that the threshold voltage of the transistor is not uniform anymore. So FinFET transistor that you will also see in one of the next slides is the solution to that. So I will go into detail later, since FinFET is solving several issues, also this one. So when we decrease the channel length, so here we can see the drain and source diffusions. And when they are biased in the reverse diode between the N plus and P substrate. So in the normal operation of the transistor, then for PN junction, we have this space charge region around, depleted from the charge carriers. And normally still we should have the PN junction between the substrate and drain and substrate and source. And we should see the depletion region and the P-tab region not depleted. But as the channel length gets shorter, then those depletion regions get closer together. So even if we don't short the N plus regions with each other, but still this depleted region is coming close at some point overlapping. And because of that, we don't have any more control over the current that flows between drain and source. If the transistor is switched off, the charge carriers that are thermally generated, they can still move quite freely between drain and source. So one of the solutions is introducing a so-called halo implant, which is higher doped region, somewhere well under at the bottom part of this N plus region. Higher doped means that what happens with the space charge region? For higher doped junction, it gets narrower. So with this higher doping, we reduce the space charge region and the leakage current gets smaller. But the FinFET transistors, that's another new modern device that is used from, I think, 22 technologies downwards. It's always FinFET. Then they are wrapping the channel around, so the gate is not only on top, but we have it on all 3 sides, and the control is much easier. So also we can access the regions deep under, what we can see here as deep under the channel, we can much easier access it and control, thus reducing the leakage current. Then the third challenge is the velocity saturation. So maybe you remember the topic of the charge carrier transport. And then we have this drift velocity, which is increasing with the increasing electric field and proportional to the mobility. So we had this proportionality factor. However, if the electric field gets very high, what happens in the scale technologies, because the power supply, it decreases a little bit. But from one technology to another technology node, we might see like half smaller feature size, or 75%, but the supply voltage will be only 10% smaller. So the scaling of the supply voltage is much less aggressive than the scaling of the dimensions. So let's say it has almost not changed the supply voltage, but we have reduced significantly the channel length. And then what we can see is that electric field, it gets higher in the transistor, the volts per centimeter. And we observe this velocity saturation, which means that mu, the mobility, is not anymore constant, but it's reducing. So the mobility of the transistor is worse. So even though we made the channel length smaller, but the transistor is not better. So that doesn't make sense because it costs so much money and we have to do something against. So something that helps is engineering of the crystal lattice in the channel by adding, for example, by adding a certain amount of doping of germanium to the silicon crystal. That creates certain tension in the crystal, and that changes the mobility. It changes mobility of holes and electrons and in the opposite directions. That's why for p-channel MOSFET and the n-channel MOSFET, this engineering of so-called strain applied on the channel is different. For p-MOSFET, we need a compressive strain, and for n-channel MOSFET, the tensile strain in the opposite direction will be beneficial. So one way is the germanium doping, but also there are some special liners applied on the gate which also change the tension, and correspondingly the mobility can get improved. Challenge number 4 is the tunneling. Increased leakage current, but now we don't speak about source drain leakage current, but the gate leakage current. From gate, it will leak to substrate, to source, to drain, also depending on the biasing of the transistor. So the oxide has been thinned. With the thinner oxide, the gate capacitance is increasing. And that's what we wanted to have for better, higher COX. Then we have also higher mobility, higher drain current, faster transistor. However, at some point, when we have started at over 20 nanometer gate oxide, silicon dioxide, then going through 15, 12, 10, 7, 5, and at 3 nanometers, we already can count individual atomic layers of the silicon dioxide there. It's not anymore a good insulator. So there is the tunneling leakage current, and when I was looking on the progress of some technology nodes, I could see that at some point it was as much as 10 to hundreds of picoamps per micrometer. It was not the peak because also it was different for p-channel, n-channel transistors, and at some point it was really disturbing for making a good design, and not only for analog design, but for digital chips, the big chips, the power consumption was enormous. So you can calculate if there are some millions of transistors, each even at the minimum size, on the chip, and then multiply it by this 10 to 100 picoamp per micrometer. So you need to get the total area of the gate on the chip, but it will come to milliamps at some point. And in order to avoid this milliamp static current consumption, because that's not because of switching, but just static, what has been done is introducing new type of the gate oxide material. So rather than the silicon dioxide, it's hafnium dioxide, or there are also other materials, something I think also including zirconium, but I haven't included all the details. These materials are so-called high K, because kappa is also used as a symbol for dielectric constant, so high K, at the same time metal gate. That's why we call these technologies HKMG, high K metal gate. So high dielectric constant means that we can make thicker transistor and still having the same oxide capacitance. And then the leakage current with the thicker gate oxide, we have more atomic layers, and with the good quality oxide, the leakage current is much improved, is much lower. The challenges 5 and 6 I group in a single slide. There wasn't a very conceptual picture I would like to add here, but I would like to explain what happens with the interconnections. So first thing, the dimensions of the transistor decrease, as I already said. So metal, we need to make thinner, especially the lower metals that are close to the transistor. So we need to separate what connects to source, what connects to drain, so those metallization needs to be narrower. Also we have the power dissipation per unit area. It's pretty much constant because we have smaller transistors that each consumes less, but then we have more transistors per unit area. So in total, we have still very high power consumption. So what can be done? First thing, if you analyze how the technology scaling progresses the number of metal layers, with 350 micrometer process nodes, we see 3, 4, sometimes possible 5 layers of metal. Now, when I look on the 16 nanometer technology node, we have 13 layers. So if we need at some point to have a very low dissipation of the power, we stack on top of each other several metal layers, and that's how we can achieve that. But also, of course, the interconnections are much more complex, so also we benefit in many other ways from this large number of metal layers. Second thing, that was on our graph of the transistor scaling as a function of time. At some point, we saw that the copper interconnection was added. Ideally, we would have had it long time before, but aluminum is much easier to process, and copper is technologically completely differently solved than what I have been showing in the process steps, because we, there were many complications. One of them is related to the electrochemical properties, that copper is much easier, the atoms are much easier diffusing in the materials. So it's not so integral. So it also needs some liners. But also deposition of copper and removal of copper, it's very different than for aluminum. So it took a long time until the industry was able to do this. The second issue related to scaling of the metallization is the fact that when the wires get narrower, also we want to put them closer together, and then there is this smaller spacing, higher capacitance, and more coupling. So in order to avoid that, there is also a trend of changing the dielectric material, but in the opposite direction than for metal, than for gate. In this case, we want to have low dielectric constant material so that the capacitance gets smaller. And now, after mentioning these challenges and speaking many times about FinFET, let's have a look at the concept, what it looks like. So first, again, reminder, the scaling of length. And we have in the right-hand side of the slide, we have the planar transistor, where the length is scaling. And what is shown here, it's not up to scale. It's not really that, but still conceptually, we can see that the length is getting narrower, shorter and shorter, but the N+ region, it extends quite deep in the substrate. And at the bottom of the N+ region, we don't have control. The gate applied potential doesn't control what happens at the bottom. So one thing was adding this halo implant with higher doped points at the edge of the implant, of the N+ regions. But second thing that was just completely new technology for production of transistor is this wrap-around gate. And what we can see is there is the N+ regions in this three-dimensional structure, and then the gate goes like that on one side, on top, on the other side, and further. This kind of transistors can be done in the substrate, but it can be also done as silicon on insulator, where at the bottom side we also have insulator, and or as nanowire, it could be also controlled on all sides. Very often we call them tri-gate transistors, because in some technologies at the start they would be made in the batches of 3 fins. And this technology has started with below 32 technology nodes. At that time, there was, right now in the, I think since 14 technology node, 14 nanometer, we only have FinFET. For some time, we also had several generations of so-called FD-SOI, fully depleted silicon on insulator. And to introduce you to this other important technology that was specifically developed by ST Microelectronics, I would like to go again a step back, more general concept of silicon of insulator, where the active part is insulated from, so electrically isolated, in fact, from the substrate. So it's much better isolation than STI. We have reduced parasitic capacitances, and above all, it's very robust against latch-up. So, for example, space applications where the latch-up is being very critical topic, they very much prefer investing in these slightly more expensive technologies, but much more robust. And so what we can see is that there is the substrate, then we have the layer of silicon dioxide, and then we have the separate NMOS and PMOS transistor. There is no way that they can latch with each other because there is no P and parasitic thyristor structure in between them. And then based on this development, there was this fully depleted SOI, which was also possible to adapt for solving these challenges of scaling making the channel length more and more short and not being able to control the gate. So in the planar transistor, the N plus region extended quite deep in the P-well. Here it's a very thin device. And also at the bottom, the P-well, there is the backgate bias, which usually it's one bias for a group of several transistors, but by applying higher or lower voltage, we can also control whether the leakage current will be a bit worse, but the speed will benefit, or we will have a bit slower transistor, but with very low leakage current. And this technology, as far as I know, worked at least down to 14 nanometers, but I think from 14 nanometers, maybe there are some exceptions, but I think from 14 nanometers, we only see FinFET, so the other device with the 3D structure. I'm not going to do presentation of this slide myself, but this is a kind of suggestion. If you're interested in the scaling trend, I place here the link to Europractice IC website. So this is a kind of silicon broker company, but also it's very much supported by European Union, and they offer multi-project wafers. So for research institutes, universities, but also smaller companies can make prototypes of integrated circuits in different technologies and not paying a lot because the mask cost is being shared. So that's the general concept behind. But also what's great is that there you can see overview of some technologies that they make available for use. You can see a list. And for example, there is TSMC, UMC, X-FAB, ST Microelectronics, Global Foundries, IMS, also photonics producing companies, which is also a new trend that we can see more and more of photonics and integration with photonics. And then you can go to details, general, like top level details of these technology nodes, but good enough to have some general idea of the scaling and also what's available, what new features come with every next technology node. So you can choose one technology. For example, there is a link to one of them. And then you can look at the different process nodes from this foundry offered and see how the core voltage has changed, because for each technology node, it's given what is the supply voltage or several maybe supply voltages. Very often we have also high voltage options. Then the number of metals, number of metal layers, it's also given. And also there are some additional features. So what other things are becoming available? Some special devices or memories, lots sorts of things, and it's in such a compact form that I just can recommend to have an overview of what's not the newest, because there are still some process nodes, some technologies that are not available for these niche applications, but we hope that it will be available soon. So I think it's at least down to 16 nanometers currently, as I'm speaking today. So in technology scaling, the trend of reducing the transistor size, we see already it will have its limits, and it's continuous discussion what comes next. Well, what's already started to come is the 3D integration, and that's something that we have observed over last at least 2 decades in different forms by stacking 2 packages on top to start with, stacking dies. So one silicon die on top of another, or also that enables this kind of stacking, some hybrid technologies with sensors or power electronics, which use different than silicon power semiconductor. And also monolithic 3D IC, as well as some combinations with system on package with complex packaging that I also mention in few words. One that you can see here as an example is the stacking of 2 dies, and in order to bond them to each other, but also have availability to bond the die to the outside of the package, we need to, for the top die, we need to have access from both sides. So there is this so-called TSV structure, that's electrical connections through the whole silicon. And that's one of the big progresses that also happened in the last years on making these TSVs more reliable, cheaper, and with less parasitics, so that we can operate faster. For some reason, I'm starting now here from the back. The 3D integration inside the monolithic. So there is project CoolCube CA-Leti, as well as 3D CMOS IEDM, where what we can see is on the same silicon die substrate, we have first P-channel transistor, and on top of that, the N-channel transistor. I don't know if there are some technologies that invert the order. Technologically, it's already very complicated. And there might be some reasons why it is in that order. But generally, it's fixed. Lower layer, it's 1-type transistor. Higher, it's, let's say, N-channel. And then there is also horizontal routing, vertical routing, as well as so connection between the stack is this vertical routing, and the horizontal is just as usual. It seems like a trivial idea. Why haven't we done that before? So when looking at the different processing steps for how the transistor is being made with growing of the oxide layer, doping, adding the metallization, and so on, we could see that some processes that need, for example, annealing, or in order to deposit additional layers of silicon, so that, or including germanium, which is also epitaxial growth, that needs to happen at high temperature. Diffusion, implantation, thermal growth of oxide, that all needs temperatures that are in the range of 900 to 1,000 and a bit Celsius degrees. So if we do that, we cannot make a process step that is low temperature and then again high temperature. So once we have deposited layers of metal, it's easy to destroy them by making another transistor on top, which needs again high processing temperature and to keep everything reliable. So therefore, what you can see here is the bottom MOSFET is the standard processing, and the top MOSFET is the low thermal budget. So this thermal budget, that's the main challenge in making those transistors, But I'm sure also testing and reliability is much more difficult because we cannot so easily access the terminal and also do failure analysis in such structures. Nevertheless, it becomes so. Since the time I was doing this lecture, I was following the developments, and also in the most recent publications, you can see how it progresses and soon plans to go in the market. Then the 3D integration by integrating two dies together with true silicon via. So it's also possible to put one die on top of another and make wire bonding, but that would be quite old, and some things would not be possible at all. Like, for example, we have detectors for imaging, where the detector can be done from any kind of semiconductor we need, but the readout is made of silicon. And if we would like to connect pixel to pixel with readout pixel to pixel, the best arrangement is to stack them on top, because then we can have module, and then next to it another module, and like that we can make also large panels. So that's an example where it can only go through silicon vias. But also memories, they use a lot, the multiple stacking of that, and many other applications. So perfect TSV, it should be small. It should be able to go deep so that we don't need to thin the substrate, because that's always tricky. The substrate is difficult to handle. The more we thin the silicon, it starts to bend, and it's really difficult. But also, the deeper it goes, the smaller we can make it. We would like to have it with high density, uniformity of dimensions, and no voids, so that we have to fill it uniformly with metal so that it's conducting with always the same conductivity. And this conductivity we want to have as low as possible. What should be mentioned also, the vias have to be made in such a way that they don't have large capacitances. All that makes it quite challenging. And here I'm showing some additional topics related to TSV. So how this is made so that also the metal is not migrating into the substrate. So there has to be constant diameter, then it's filled with metal, and in order for the metal not to migrate into substrate, there is the barrier, that's the green layer. But the barrier, very often, it will not have very good properties of creating a good interface with the deposited metal that we would like to have, for example, copper or aluminum. I don't know which one it is. And similar, like making the vias in the normal processing, we have the lining of tungsten. Similar here, we also need to have this seed layer, which enables a good attachment of the initial layer on which the target metal layer is deposited. So the metal is deposited in a cavity, and the cavity is either prepared by etching or by laser drilling. And there are two ways of making this cavity, either through deep reactive ion etching, where the whole wafer is handled at the same, is processed at the same time, but it's not as perfect, uniform, and repeatable. Or we can do that by laser drilling, but then it's a time-consuming process because we have to basically drill one by one. So these are the two options, and depending on what is the purpose, one or the other can be chosen. So for the 3D integrations, these are the most important steps that I have presented, and let's see what we see next in the future and which of these technologies will be more important.
You're the signal in my static hum, a perfect match we've overcome. Wires cross but we still